disk, because if dust comes in, then you can basically throw away your hard disk. So I concentrated my efforts on the other side of the hard disk, the printed circuit board. And as you can see, they're not that big, and they have like in 3 or 4 chips on them, and they all seem pretty simple. And I took my stack of hard disks and I took the PCB from each and every one of them, and these were the chips I found on them. Well, first of all, there's this one, and you'll probably recognize this if you ever build a PC, because it's a bog standard RAM chip. It's either SDRAM or DDRAM, and it comes in a few different flavors, but this is basically a jelly bean part. You can just throw the type number into the internet and you get a nice data sheet. They're also pretty boring. They're just bits of RAM ranging from 64 megabyte down to 8 megabytes, and they're usually always the same as the cache size advertised on the hard disk. And also some of them don't have them on board, but built into the hard disk controller itself. Okay, next there's this chip. It's usually at the top of the board, away from the SATA connector. And what it is a spindle motor driver. It's basically the controller that makes sure that this goes round. Pretty important. ST seems to make most of them. Datasheets aren't really available, but other chips in the same family do have data that's available. So it's possible to somewhat figure out what they do. But most of the things they do, it's just basically they make the spindle go round. So it's still not interesting. Then there's this little chip. It's also not on every hard disk, and this is a bit of flash memory. It's also a Jelly Bean part, and it's made by a few different manufacturers, and it contains the boot ROM for the disk. It contains the code the disk executes to start up, to make everything go around, to load the initial stuff, etc. And also sometimes, especially in earlier hard disks, it's integrated in the controller of the hard disk. Okay, and finally, there is this big one, smack dab in the middle, next to the SATA interface, and this one is the hard disk controller. And of course, with the only big chip remaining, all the logic of the hard disk has to be in here. Unfortunately, this chip is made by a few people, well, mostly Marvell, as you can see. But also ST makes them, and at least Western Digital and Samsung also designs and makes their own hard disk controllers. And finally, there were those little guys, and you may have seen them if you ever destroyed a hard disk yourself, and those are piezoelectric shock detectors. And according to the datasheet, they can part your head or something when your hard disk falls. More likely, they'll just set a bit in the firmware somewhere saying, hey, your warranty is void, go buy a new hard disk. Okay, this is how everything fits together. We've got, okay, it's invisible. We've got a SATA port here. We've got the hard disk controller in the middle, which is directly connected to the flash memory to boot from, also to the DRAM memory, the external RAM. It's also connected to the spindle controller, and the spindle controller controls, of course, the spindle motor, and also has some AD converters which are used to read out the shock sensors. Okay, so the hard disk controller is the most important thing, and I would really like to have a data sheet of one of those. So it's pretty easy. You go to the manufacturer's website and you enter the part number in the search box, and then you get a lot of data sheets. Is it? Is it? Well, of course not. And it's not that you don't get any data sheets. All the manufacturers don't even acknowledge the chips exist. They're not on their websites. So they're pretty NDA and secret and closed. Okay, of course we have the rest of the internet, which is fairly big nowadays, so it must have the data sheet somewhere. Well, not really. You've got datasheet sites just wanting to have hits, so they claim to have the datasheets and then come up with, hey, is this diode the thing you're looking for? We also have sellers of the PCBs for the HDs, which is good if you want to recover a broken hard disk and you have to exchange the PCB. And you have Chinese sellers of the hard disk controller chips themselves. And how they end up having the chips, I don't know. I don't want to know probably. Okay, but the internet also has some other stuff that's not datasheet related, and this is one of them. This is a story, actually a thread on a forum called HDD Guru, which is a hard disk repair people forum. And it's basically the story of a guy called Dex or Dajan. And he has broken his laptop hard disk by somehow managing to corrupt the data in Flash somehow. And he really wants to know if there's a way to either repair it or to boot from an external ROM or whatever. And of course, as usual, the thread sits there for 5 days with no reply whatsoever and is doomed to just die. Until the guy responds to himself, actually, with, hey, guys, I found the JTAG port of the hard disk. And everyone who knows what a JTAG port is laughing now, I think. For the other people, JTAG is pretty important because you can, JTAG port is a debugging port and you can actually control the hard disk controller like a puppet. You can read memory, you can write memory, you can stop the disk, you can set breakpoints, you can do everything. Okay, so the thread goes on. The guy figures out that one of the connectors that's available at most Western Digital hard disks actually is a JTAG connector. It's just that no one recognizes it because it has 38 pins. Normally you would expect like in 10 pins or something. And he also dumps the firmware. He also manages to connect to it by using OpenOCD, a program for that. He finds out there's an ARM CPU living in the chip. He dumps the firmware. He finds out that there's actually a serial port on most hard disks on one of the headers that are next to the SATA port. And finally, he, of course, manages to repair his hard disk, and he dumps a few pointers of how to do it if you have the same problem. And then he disappears into the ether of the internet. Okay, what can we learn from this interesting discussion? Well, first of all, Western Digital disks seem to be ARM-based. At least all the newer ones are. Western Digital disks all seem to have a JTAG port, which is cool. They also have a serial port, which is mostly unused with the standard Western Digital firmware, but is actually there. And the bootloader actually uses it. And, well, finally, with all this stuff added up, Western Digital hard disk can probably be hacked. Okay. Great, of course, reading about this is awesome, but I wanted to do it myself. I wanted to have a hard disk with JTAG connected to it. So I went and took all my stuff, and I got a brand new hard disk to hack on. And this is what I got. I got an ATX power supply for power, of course. I've got an FT2232H board as a JTAG adapter, and actually boards like this are obtainable for like 30 euros on eBay. And they're pretty good as JTAG adapters. They also have an extra serial port, so I could also use it to hook up the serial port of the hard disk. Finally, I used the cable to connect the hard disk to my desktop PC. And finally, I used a bit of software called OpenOCD, the Open On-Chip Debugger, which is a bit of software which talks through the JTAG adapter to the controller. Okay, but perhaps there's a problem. As I said, I bought a brand new hard disk to try everything on. The hard disk of the guy in the forum was a bit older, and it also was a laptop hard disk. His hard disk was a quarter of a gig and had an older controller, while my hard disk was a desktop-sized 2 terabyte with a newer controller. So would this still work? Well, there's only one way to find out, and that's to try it. So this is my hardware setup. In red at the top, you can see the FT2232 board, which is connected to the JTAG connector in the middle and also to the header with the serial port. And down below, you see the Flash EEPROM dangling on a few wires because I wanted to back up that first before I went hacking. Okay. So when I ran OpenOCD, I saw this, and OpenOCD basically has a mode where if you don't give it any configuration, it'll try to figure out what's on the JTAG port. And normally it would detect one tab for one microcontroller or one FPGA you have sitting on the bus. But I saw something interesting, and I actually had to try this a few times because I didn't believe it. I thought my JTAG setup was broken or something. But there are three tabs in this picture, which means OpenOCD thinks it has detected three different CPUs or FPGAs or whatever. So what is this? Do we have a 3-core CPU here? Well, actually we have. It's a 3-core chip. We have one ARM Cortex M3, which is a tiny microcontroller thing like you would find in your washing machine or something. And we have two bigger Ferocion-like cores, which are ARM9 cores, which are fairly powerful. They're like, I don't know, the chip that's in your phone only a few generations earlier. And all of them run at something like 150 megahertz. I didn't measure it exactly, but that's the order of size of speed they have. Okay, so we know there are 3 controllers in there, but what do they do? I mean, if there's just one controller, then it runs everything. But if there are 3 controllers, they may do something different. So the question is, which CPU does what? Well, the first Ferocion, and I'll just call it Ferocion 1 here for lack of a better name, it handles the disk access. And it's pretty easy to find it out because you just use OpenOCD to go into it. And then you say stop, so the execution of that processor stops. And then all of a sudden the hard disk still reacts, and you can still ask it about smart stuff. But as soon as it tries to access the disk platters itself, then the hard disk goes dead and Linux can't find it. The second Ferocion handles the SATA interface, because if I kill that, then the hard disk is immediately completely off the SATA bus. Linux throws a fit about not being able to find its hard disk, and yeah, that's basically the end of it. I later found out that it also handles the cache. It does the cache management. It also handles the so-called LBA to CHS conversion. And LBA stands for logical block address, and it's basically the way a PC requests a sector from the hard disk. And the numbering is pretty easy. It just says, okay, the hard disk has a bunch of sectors, and we're going to number them from 0, 1, 2, 3, etc. And you can just ask, okay, give me number 345. Unfortunately, the logical block address doesn't indicate a specific physical place on the platter. That's where a cylinder head sector, or CHS triplet, is for. It's a type of address that actually indicates a specific place on the hard disk. So the Ferocion 2 translates between those two. And the Cortex M3 finally doesn't seem to do anything. I can stop it, the hard disk will just keep on running. I have no idea what it's good for. I have speculated that it's for some kind of low power mode where the Ferocions are asleep, but I never have been able to prove it yet. Okay, so now we know what the CPUs do. We want to have a target because, of course, I still want to hack the hard disk, and I want to hack the CPU that I can use to make the hard disk do interesting things like modify sectors on the fly. So yeah, rewrite data on the fly. That's what I want. Few considerations. SATA, or at least in this hard disk, is 6 gigabit a second. If the hard disk would use only the controllers to move the data, then at 150 megahertz, the maximum speed, and this is an absolute maximum, the maximum speed it could have is 2.4 gigabits a second. And it's specified as something that's quicker than that. So there's something else going on. The process of reading data and sending packets over the SATA interface must be hardware accelerated. And the standard way to do it is to use direct memory access. And what is direct memory access? Instead of the hard disk logic, for example, telling the Ferocion to handle each byte that's read off the disk, the hard disk controller will just take a bunch of memory and will write the data immediately into that memory. And thereby bypassing the controller and making everything much faster. So from that, I got a nice interception point, the cache. And how did I end up at that conclusion? Well, the DMA process has to write stuff to memory. So it needs a bit of memory to keep all the data that's read from disk in. The cache is a bit of memory that also needs to have the data that's read on disk. So it would be logical for to just use the cache as a DMA target because, well, you write data to a memory location where you would want to have the data anyway. So if that's true, this is how it would work. We've got a schematic of the hard disk here. You see this SATA port at one side, which is connected to the PC. You've got Frocion 2 and Frocion 1 sitting in the disk, and you see the actual disk logic on the right. And all of them can theoretically, hopefully, access the cache, which is a bit of memory which sits down below. Okay, so now the disk gets a request. It gets the request to get sector 42, of course, sector 42. The second Frocion will then pick up that request. It'll translate it to a cylinder head and sector position, but it will also make an entry in the cache descriptor table, which isn't the cache memory per se, but is a table which describes it, saying, okay, I'm gonna receive some sectors, and I have just decided that I'm going to position them at address 123 in the cache. So it basically makes an entry, okay, sector 42 is going to live in at address 123 in the cache. And it'll tell that address to the first Frocion. The first Frocion will then do its thing and tell the disk to read stuff, etc. And the disk logic will then write the things it has read. In this case, it's just a string hello. It'll write it immediately to the cache, not involving the first Frocion in any way. After this is done, it'll tell the first Frocion, the first Frocion will tell the second Frocion, and the second Frocion will tell the SATA controller, hey, there's data at address 123 and the PC wants to have it, so go and send it. Okay, so now you have seen that both Frocions don't touch the data itself. The data is written by the hard disk logic and is read by the SATA interface. So the question is, can they actually touch the data? Because in the normal process, it doesn't seem like they do. There's only one way to figure out, and that's to test it. And for that, I need to know the memory map of the Frocion processor, because the cache is a bit of memory, and if the Frocion can actually access that bit of memory, then it's possible it can access the cache. So you find something like this by basically disassembling the code and looking at it. And what you see here is that it has access to a few bits and bobs of RAM here. It has some I/O it can access, in which all the I/O registers for the mechanics and whatnot live. It has a bit of boot ROM that it uses to actually read in the flash. And it has this huge amount of exactly 64 megabytes of RAM, which is exactly the amount of cache the memory says it has. So yeah, it's pretty probable that the cache lives there. So let's see if that's true. And to see if that's true, I took my hard disk and I mounted it and I wrote the string hello world to it. And the string hello world in hexadecimal you can see here is 4865, etc., etc. Then I started up my OpenOCD thing. I connected to the hard disk over JTAG. I did some magic to figure out a number, but you can also just search the 64 megabyte bit of RAM. And finally, I got an address. And when I read it out, I got a hex string that looked exactly like the hex string I wrote. So I basically found the place in the hard disk cache where the hello world string lived. So, in other words, yes, the Frocion, the Frocions can read from the cache. And in a second experiment, I also found out that they can write to cache, because if you modify it over JTAG, then read out the sector again, you get the modified data. Of course, we know that the cache lives in the big DRAM section, and that somehow the data read ends up there somewhere. The question is, how does it work? What logic does the Frocion use to allocate cache? At what address does what sector live? It's all pretty important information. Unfortunately, the only way to figure it out is to dump the code and reverse engineer it using a disassembler. I've used IDA Pro. As an aside, How easy is it to disassemble this code? Well, it's a double-edged sword. On the plus side, you have no intentional obfuscation. It's not like the Western Digital guys try to make life hard for you by obfuscating code or encrypting it or whatever. Also, of course, you have JTAG access. The JTAG port is a debugging port. So you can actually just start the code, stop the code, set a breakpoint, whatever. It's all pretty helpful if you want to test something. On the other side, you don't have any strings in the firmware. Normally, if you disassemble a bit of code and you're looking at a routine, you can sometimes find a string in there saying, for example, log can't open log file, something. Then all of a sudden you know, hey, this string, this routine has something to do with opening a log file. The Western Digital firmware doesn't have anything like that. So if you want to know what a bit of code does, you'll have to disassemble it and grok it. Also, the firmware has mixed ARM and thumb code, which are the two ways an ARM can interpret code. And if you don't have a disassembler that can be smart with this, you're going to have a hard time. Also, and this is this is an observation I made. I can't prove it, but it seems to me, I've actually looked it up, and the code base for this hard disk is, if I recall correctly, something like 9 years old. And it feels like the Western Digital guys just bolted code onto it if they wanted to add a feature. And it feels like the code is just, a bit of code with an extra routine tacked on here and something changed there. There seems to be a lot of legacy code in there. Okay, so yeah, disassembling took me a while, but eventually I stumbled upon something great, something I wanted to have, which is this, which are way too small letters, so I'm just going to explain you what this is. This is the description of a table that lives somewhere in the RAM of one of the processors, the second Ferocion to be exact. And it contained a bunch of entries, and each entry had the start and the end logical block address of the cache section it describes, so the bit of hard disk that's in the cache or is supposed to be in the cache. It has the amount of sectors that's actually read and written. If the entry is there, it doesn't mean it's filled yet, so you can read that from that entry. It also has a flag indicating if it's read or written or whatever. And it also has a memory location index. And this memory location index you can put into a simple formula and outrolls a certain address. And the address is the RAM address where you can find the data that's in that bit of cache. So with that information, would it be possible to find a sector in cache? Well, obviously. I mean, I just walk through the table. I see if the sector LBA is in there somewhere, and if it is, I know where to look. Can I read what's on the disk there? Yes, because the cache is supposed to have the same information as the disk. So I can just look up the bit of RAM where the cache data is supposed to be in, and I have the data. Can I modify it? Yeah, sure. I mean, it's memory. I can modify it. That's what processors do. But can I do it before it goes to the PC? And that's an important question, because if I'm too early, then the hard disk will overwrite all my interesting modifications. And if I'm too late, then the data will already have gone to the PC. And yeah, I'm modifying some data that isn't used anymore, probably. So to fix this, I need to inject code. I need to make a routine that's called in at exactly the right time. Well, first of all, I needed to write a routine that would do something interesting with the RAM. And I needed to get that to the second Ferocion. And that's pretty easy because I can just place it somewhere in free memory. There are a few bits and pieces of free memory you can use for this. But then if I just place it in free memory, then the CPU doesn't have a reason to pick up on it. I mean, it's just doing its normal thing, and it has no reason to actually look in the free memory. So what I need to do, if I do that, it won't be run. So what I need to do was make a hook somewhere. I needed to have a routine that was executed in exactly the same time, and I would need to find a way to run my code from that. And something like that is called a hook. And I'm not going to bore you with the assembly, but I'm going to give you an analog. And the analog is this. It's a cookie recipe. And it's a very basic cookie recipe. It's boring. And I don't want boring cookies. I want chocolate chip cookies. But I'm not going to rewrite the entire recipe because, first of all, I'm lazy. And second of all, if I were to do this with the hard disk, I would have to rewrite the whole hard disk firmware. And I'm not going to do that. So I'm going to be lazy. And I'm just going to add a second bit of paper with the extra ingredients. And of course, I can just use this, but then I would start with the cookie recipe, and I wouldn't know where to actually add the extra ingredients. So I need to have a pointer when to go to the second bit of paper. And the way I do that is I just modify my first bit of paper, and instead of one instruction, in this case add sugar, I'm going to say, okay, go and see. See, this is pretty small. I hope you can all read this. What I did out in the instructions was cross out one instruction, in this case add sugar, and instead of it I put an instruction to go read the second bit of paper, and the second bit of paper then of course contains all the extra things I need for chocolate chip cookies, and at the end I can just continue where I was. And finally, I will have chocolate chip cookies without having done too much writing. So that's basically how a hook works. And in ARM code, it's, well, about the same. So of course, I wanted to try it. And this is a bit of pseudocode that describes my first hack. And if you can't read pseudocode, this is pretty simple. What I do is I walk the cache table, I find every single sector that's in the cache table, and I write 1, 2, 3, 4, 5, 6, 7, 8 to the first 4 bytes. Pretty simple. So I wrote the code, I wrote the hook, I went back to my OpenOCD program, and I used JTAG to stop the processor, load both the hook, which is at the top here, and the program, which is here, into the memory, and then I would just resume the CPU like nothing has happened. So if everything is well, now each sector I would read would contain 1, 2, 3, 4, 5, 6, 7, 8 as the first 4 bytes. So the way to test it is just to read a sector, and as you can see, it neatly has 1, 2, 3, 4, 5, 6, 7, 8 as the first 4 bytes. So my hook actually worked, which is pretty great. Okay. The problem is, if I have a hard disk with a bunch of wires on it, which needs JTAG to reinstall the hook every time I want to restart my PC, that's not going to be a good black hat thing to work with. I mean, I can see myself going to Facebook headquarters with a hard disk with wires sticking on it with instructions to please reinstall the hook. Somehow I don't think they'll be too kind on installing it in their servers. I don't know, it's a feeling. So what I need to do is make it persistent. I need to modify just once and then make the hack come back every time the hard disk reboots. And for that, I need to put it in a bit of memory that doesn't lose its contents when the power goes off. So a nice candidate for this is the little chip in there. I've introduced you to it earlier. It's the bit of flash that contains the boot data for the hard disk. And what I did is, you also saw this earlier, I desoldered it and I put it in a bit of Vero board with headers, so I could easily take it off and put it into my programmer. So I could easily read it out and rewrite and put it back in the hard disk. Okay, the problem is the flash doesn't have raw data that's put in memory somewhere. It has a very specific format. It's basically a bunch of blocks with in front of it a table, a header table describing each block. And I didn't have to figure this out myself. The information is on the internet. You're advised to use Google Translate for it though. Okay, so the format for the flash header is pretty simple. First of all, it has the type of block. Somehow there are different types of block. I'm not sure if it's important, but it's there. Secondly, it has the compression type, because flash is really expensive and it would cost maybe, oh, I don't know, cents to put a bigger bit of flash in the chip. So what they do is compress the data on it, and they have two compression types to do that. They also have a way to do it uncompressed, by the way. It also contains the position of the block in flash, which is pretty important, and also the position in memory, in RAM, where the decompressed block should end up. And finally, it has an execution address, and only the last block has this, and it's basically an address where the bootloader jumps to as soon as it's done loading and decompressing everything. Okay, so with all this information, I needed to make a tool to do this for me because, as I said, I'm lazy. So I made a tool. I unimaginatively called it FW tool for firmware tool. And what it can do is it can disassemble a flash image. It'll just give you separate files with the separate blocks in it. And it'll also dump a text file describing what's in the headers. You can then modify it, and then you can run the tool again, and it'll repack everything into a single firmware image, which you can then put into your flash, and your hard disk will just accept it. There's one problem, though. As I said, some of the blocks are compressed, and I have no idea what the compression algorithm is. So I cannot modify the compressed code. So I cannot insert my hooks directly into the flash. What I can do, however, is I can add code, and I can just tell the bootloader, hey, this code isn't compressed, just copy it over to RAM and you'll be fine. And what I then can do is I can modify the execution address, so it'll execute my code first, and my code can then insert the hooks into the now decompressed code. So that problem is solved. And the results, again, sorry, pretty boring picture, is exactly the same as before. But this is on a hard disk which doesn't have a JTAG connector to it. It has just a desoldered, reflashed, and resoldered bit of flash. Still, this is not enough because last time I checked, Facebook doesn't accept hard disk donations, and they'll probably not accept it even more if they saw the flash chip was desoldered and resoldered. So that's not going to fly. So what I needed to have is a way to reflash the flash chip on the fly, using only the software, using only the SATA port, and preferably in some way that I can do it remotely. So that's the question. Can I reflash the hard disk remotely? There are a few examples there. The biggest is the Western Digital firmware updates. Sometimes hard disks have firmware updates, and they also update the flash chip that's in there. The hard disk firmware tools have been reverse engineered, and they use so-called vendor-specific commands, which is a reserved section of the ATA command set for vendors to do what they want with it. And of course, those commands are pretty well documented. Not unfortunate. So they had to be reverse engineered. There are a few tools that can actually talk the vendor-specific commands. There's a tool called mHDD, and there are a few scripts to read out the flash for a hard disk. I actually found a paper called Hiding Data in Hard Drive Surface Areas, which is about storing data in the bits of hard disks that are usually reserved for the firmware. And they also use vendor-specific commands to write that data. And finally, there's a tool set called idle3 tools, which is used. Western Digital green hard disks, unfortunately, have they go into sleep after a certain while, and that doesn't always work with Linux. So Western Digital made a certain tool to disable that behavior. But of course, you would need DOS to run that tool. Someone actually managed to reverse engineer it, and they ported it to Linux. And now it's a pretty nice program, and it actually uses the proper Linux SCSI I/O controls. And it doesn't do anything per se with the firmware, but it does use the vendor-specific commands to set the flag to enable or disable that behavior. So with everything I saw, I decided to add some code to a firmware tool. And now it could not only disassemble and reassemble a flash image, but it could also read the flash from an attached Western Digital hard disk, which is just attached over SATA, like you normally would have. And it could also write the flash back to the hard disk. And all this while the operating system is just churning along. So that's pretty useful. And now my evil plan was basically complete. A hypothetical attacker could basically own a box. He would use a zero-day exploit or an unpatched something to just get root access on the hard disk. And as soon as the guy has root access on the hard disk, he will read the firmware from the hard disk. Sorry, has root access to the box. He'll read the firmware from the hard disk. He'll modify it with the hacks I just described. And he'll then write it back again using, for example, FW tool. Then, of course, as owners want to do, the owner finds out that his box has been hacked. He's very angry. He's disappointed. He reinstalls his complete operating system. He perhaps switches operating systems. He patches all his vulnerabilities, and he's absolutely sure that he now has a perfectly safe box, which is completely true on the software side. But of course, not on the hardware side. So the attacker has just modified the hard disk's firmware, and the hard disk is now looking for a specific magic string. And as soon as this specific magic string is written to the hard disk, it'll enable a bit of code. And writing a string to a hard disk is pretty easy if that hard disk sits on the internet. If you have a user account, you can just log in and make a file with the trigger string in it. But if it has a web server, you can, for example, just request a URL with the trigger string in it. The URL will eventually end up in the web server's log files, which will be written to the hard disk, which will then know that the trigger string has been sent. And it'll then activate a bit of code, and that bit of code will then, from then on, every time it sees the file /etc/shadow coming along, it'll modify it. And /etc/shadow, for everyone who doesn't know, under Linux and probably a whole host of other operating systems too, this keeps track of the passwords for every user, including the root user. That's a pretty important file. And now the hard disk has decided to change this file into something the attacker has set earlier. For example, change the password hash for, I don't know, root. So the attacker then just uses SSH and logs in as root and enters his own password. And the box will then check that password against the shadow file, which has been modified. And the attacker's in. So that's how an attack would work. So then the box is completely re-owned. The attacker will install his porn server, media server, and yeah, it is done. And now I would like to give a demo, but unfortunately the hardware doesn't seem to be here yet. So, okay, so I hope I can show video on this MacBook. It's unfortunately I brought stuff for a nice live demo, but I can't show it. Awesome. Just a sec. Okay. Macs, how do they work? No, I do not want to close stuff. I want this, and I want this stopped, and I want this full screen. Okay, so is this readable for everyone? I don't hear any complaints, so I hope it is. Okay, this is a terminal screen made on my workstation, and I'm SSHing into, I can show you, into this little box, which is my server, which is a perfectly flat 1-unit server, as you can see, with a hard disk that's a bit too big on it. And I'm just going to log into it as my own user. And let's pretend I don't have the root password for the system. By the way, this is a box which already has had the the hard disk flash treatment. So the rogue firmware is already in there. Okay. So I'm in as my own user, but I don't want to be my own user. I want to be root. But as you can see, I don't know the password. So Sue will just throw me out. Okay, now I'm going to turn on the hack. And to do this, in my firmware, this is a two-step process. First of all, I need to tell the hard disk to actually enable the hack. And secondly, I need to give it a password. It needs the shadow file to have as a root password. So now I execute those two steps. And now actually the hard disk knows that if it has a shadow file on its hands, it needs to modify the root password that's in there to test123. You can see it there. There. Okay, unfortunately, Linux still has the shadow file in its cache, and I need to push that out because as long as Linux has the shadow file in its cache, it'll check the cache instead of the hard disk, which we want. So I do this, that in this case by just generating lots and lots of disk activity. And on a web server, this isn't needed because a web server or another server usually has enough disk activity by itself. So the shadow file will eventually be pushed out of the flash anyway. So this is gonna take a while, I think. Second. Dan kan ik de tweede demo tweede kan ik live doen. Okay. Sorry, it's still clearing the cache. I just stopped it from clearing the cache. And now the cache is cleared. I can just log in, and the system will get the shadow password from the hard disk, which is faked. And well, you can't see it here, but I'm entering test123, and as you can see, I'm in. Okay. Okay. Now I hope I can get back to my presentation. Yes. Wow, it works. Okay, of course I've shown you the what I would do if I were an evil hacker, but I'm not. I'm just trying to do this to hardware. I'm just demonstrating this, and I'm just trying to exploit this as a way to figure out how a hard disk works. But there are also things you can do. Hardware, awesome. Wait. You know what? I'm just going to use the arrow keys here. I think just a second. Okay. So there are also non-evil uses for this information. For example, you can use a hard disk that has modified firmware. You can use it as an uncopyable disk. For example, you could modify the firmware so it would act normally if it sees that the sectors are just accessed randomly like a normal operating system would do. But as soon as it notices that that every sector it has gets read out linearly, so starting with 1, 2, 3, 4, etc., it can detect that and it can throw a fit. For example, it could report bad sectors, or it could report completely broken data or something. So you could do that with modified firmware. You could also use a hard disk, even just a bare platter, as a universal SATA client. I mean, you've got a bit of hardware that can speak 6 gigabit a second, which should be pretty useful for a lot of things like scopes or whatever needs to interchange lots of data at once. And you can also use it as a generic microcontroller board, which is pretty useful. Yeah, if you just have a broken hard disk and you just got the platter for free. So say you would use it as a generic microcontroller board. What would you get from it? Well, of course, you would get the 3 cores to play with. You get lots of RAM. In my case, I have 64 megabytes of RAM only in the cache, plus a few bits and bobs in the chip itself. The whole thing is flashable either over JTAG or serial, or if you keep the firmware intact, you can even flash it over the SATA port. And you'll have quite a bit of I/O, namely 2 times SPI. You've got a UART for the serial port. You've got some generic I/O pins, and you'll even get more if you can figure out how to control it, of course. So I wanted to demonstrate this, and I hope I'm going to be able to do this demonstration in hardware because it's way more fun than just showing a video. And I did this by installing Linux on my hard disk. Okay. So to quote the words of a great guy, guys, I'd like to take a minute. Just sit back there. Okay. We have. Yeah. VGA. We have power. Okay. Do we have video? Hey, it's video. Oh, I really hope I'm going to be able to pull this off because I just noticed that, of course, at this presentation, one of the pins have broken off. Murphy, thank you. Okay. Okay, so if my network cable would be connected, then I would now be able to log into my server. Well, at least that works. And I should be able, if the rest of my hardware cooperates. What you see here right now is on the top is just a command line shell on my laptop, in this case, which is an SSH to my server. And on the lower screen, you see a serial port connection to the serial port of the hard disk, which of course has great trouble with actually working. Yeah, just a sec. Okay, I'm basically holding on to the wire with my finger, so if this breaks, I'll just move to the video. Okay, yeah. The output you see right now is the debugging output from my firmware, and it'll just show you the cache description entry that's going on. Okay, first we need to enable the hack, like I showed you before. And if the oh, please work. Okay. Again, thank you, Murphy. No, I fear I'm going to have to switch to the video. I'm really sorry. Yes, I have. It's the root file system, so it should be mounted. But when I just showed you the hard disk, I think I may have messed something up. Okay, to the movie. Let's see. Okay, in the movie you'll see about the same setup. If it works, yes. My console on top, this is my workstation. And the serial port on the bottom. And let's see. First of all, I mount the hard disk because I need to do it in this case. It's my workstation. You see the debugging data on the bottom. and I see that it actually cuts off a bit of the video, so I'm just going to move it here. I hope this is clear. Okay, now I'm going to tell the hack that it should go live, and you'll actually see it respond with a smiley, which just scrolled away. Now I'm going to copy a certain file with an encoded Linux kernel to the hard disk. And the end result is that this ends up in cache. I'll do the same with the initial RAM disk. And I'll then give the hard disk the command to assemble all those things from cache into a contiguous Linux kernel and init RAM disk. And finally, it should actually run the kernel. So you see it now assembling everything. Thank you. And as you can see, I didn't actually manage to find an MMU-less root file system, so it crashes. But the proof of concept is there. Okay. Now I actually want the Mac back. Can we switch back to the Mac, or do I have to do something here? I can try to do something here, but I don't know Macs. Yeah. Or you just plug it in. Okay, yes. Okay, so that's basically the last slide. What I wanted to show you is this. If you want to know more, I actually documented this on my website too. So if you go to that URL, you can read everything I said. I'll also put on parts of the software I used. I actually ripped out the bits that actually modify the shadow code because I don't want to be responsible for the hacked hard disks that somehow do something evil. You can also contact me. I'm Jeroen@spritesmods.com, and on Twitter I'm spritesmods. So finally, are there any questions about this?
Please line up to the mic.
Yes, people, go ahead. Sorry, I don't hear you.
Oh.
I'll just walk to you. Okay, knock yourself out.
Hi, Jeroen. Thanks for a lovely talk at just the right pace. When you run into JTAG, you get happy. When I run into JTAG, I've had it a few times with a TI DSP, and it had crummy behavior. It didn't work. It didn't do anything. Was I missing something, or?
Sorry, I didn't hear it quite well, but you're asking why I got the JTAG thing down as quickly as I did? Is that right?
Yeah, don't you need extra specification for that? Because the cases I tried JTAG, it just didn't work.
I don't know. I think I just was lucky. There was a bit of research involved with me figuring out that the JTAG IDs I got back actually were for Cortex M3 and Frosium-like things. But apart from that, I just connected everything and it worked. So, yeah, sorry, Magic Pixies, I don't know.
So, like you said, you were facing the cores whose JTAG access is actually documented, and the TI DSP, basically the only thing documented about them is the length of the instruction register, and that is it. There is no documentation on it whatsoever. So, read only? No, I know that. I mean, if you use Code Composer Studio from TI, you can probably debug the DSP. So if you want to not have to use their software, I would say start by sniffing that.
Okay, thanks.
Okay.
Just take it to edit.
What did you use as a point to hook?
Sorry again?
Where did you install the hook?
I installed the hook in a bit of, I disassembled the firmware and I tried to understand the firmware up to the point where I could find the routine that actually instructed the SATA board to read the data from the location in cache where the data is. And I basically just put the hook at the start of that routine. So instead of just pushing it out the SATA port, it would modify it first and then continue pushing it out the SATA interface. Does that answer your question?
Yeah, okay, so probably in some interrupt handler or something. Or an
Sorry?
event, so probably in an interrupt or an event handler.
I guess it would have been an event handler. It wasn't in interrupt mode, so yeah, something like that.
Okay, thank you.
You're welcome.
About the Cortex M3, have you tried put a breakpoint on reset and then just do a soft reset to see? Because it would not surprise me if the Cortex M3 is responsible for bringing up the
Sorry,
firmware.
I have to interrupt you. Sorry, it's pretty hard to understand what you're saying from
sorry.
here because of the audio installation.
Have you tried putting a breakpoint on reset in the Cortex M3? Because it would not be surprising to me if it is responsible for bringing up the chips, bringing up the ARM9s.
No, I don't think it's responsible for bringing up the ARM9. At least it looks like the ARM9 can do that all by itself, and it also loads in the SPI data itself. It may be true, but it doesn't feel like the M3 is responsible for that. Sorry, I can't give you a more specific answer than that.
Yeah, have you found out anything interesting about the peripherals around a chip? I mean, like controlling the spindle controller or the SCHTA interface or something like that?
Yes, actually, I have figured out the spindle controller because, as I said, the spindle controller I had was undocumented. But if you take a spindle controller that's one lower in the part number, then you get a nice data sheet with everything in it. I don't actually have tried. I thought about, but I never ended up doing it. I wanted to try what would happen if I would tell the spindle controller to move faster. Perhaps it would be possible to overclock my hard disk, but unfortunately, I've never tried it. So that's left as an exercise to the listener. And if you actually manage to do this, I want to hear about it. Okay.
Have you actually looked at the vendor-specific commands and what is preventing them to be run as a normal user and only as root?
I think you can't use the I/O controls. You need to send ATA commands directly to the hard disk as a user. So you need root access for that.
Okay.
Okay. Just one.
Hi, another question. You said you're looking for some magic string to trigger the attack, but that means you have to look at all the data that is written onto the hard disk. And as you said, usually it's done via DMA, and the data does not go to the Ferocians. So if you want to look for the magic string, you have to look at the data, and this degrades the performance of the hard disk. So wouldn't someone who reinstalls his operating system on the system that was broken somehow get the feeling that something is wrong because the performance is off?
I actually was hoping someone would ask this question because it means you have been paying attention. I actually lied a bit. What I do is I check for the magic string on the start of every sector. So I only need to check every word in every 512 bytes. That doesn't seem to degrade the performance and too much. And if it would, I could just move the granularity down a bit. And it would mean you would have to spam the magical string to the server. But hey, what are 1,000 HTTP requests among friends, right? So.
Okay. So.
Yes. Thanks.
So can you think of other ways to trigger something there than like writing to a specific file or something? Or
in theory, you have access to all the sectors that are read. So if you want, you could even implement a complete file system interpreter for it. Yeah, it's basically limitless, or actually it's bound to what you want to implement in the firmware. So yeah.
Okay, thank you.
Okay.
Hi. So
Hello.
if I've been paying attention and the piezo controller is actually some kind of an accelerometer, gyro.
Yes, something like that. I think
Alright.
it's like one of those piezo discs. If you hit it, it'll give a
Alright.
signal. It's
So
not really
it-
sensitive, I think.
All right. So maybe we're a bit removed yet from 8-core quadcopters based on old hard drive PCBs.
Well, the power is there, of course, and you have SPI. So I don't know.
All right.
Try
let's
it.
get cracking.
No more questions? This will conclude this end of this wonderful talk, and let's give the speaker another round of applause.
Okay.